So my talk, I'm not going to bother introducing myself. So I'll just get right to the talk. And my talk is entitled, Is the Universe Made for Life? Anthropic Coincidences and the Multiverse. Now, is the human race meant to be here? Or are we just a fluke in a meaningless universe? There are two very widespread and diametrically opposed views on this question. One is held by Christians, Jews, and other theists, and the other is held by most non-religious people, including atheists. What is the Christian view? According to Scripture and Catholic tradition, we definitely are meant to be here, and the human race has an important part in the divine plan. The letter to Diognetus, for example, a Christian work of the early 2nd century, said, God loved the race of men. It is for their sakes that he made the world. The first creation account in the book of Genesis reaches its climax with the creation of mankind. And the Apostle Paul told the Ephesians that they were chosen by God and destined to be his sons and daughters, quote, before the foundation of the world. On the other hand, many atheists tell us that science has shown the human race to be just an accidental byproduct of blind material forces in a universe that has no point or purpose. Bertrand Russell wrote that man is, quote, a curious accident in a backwater of the universe. A classic statement of the atheist view is given by the physics Nobel laureate Steven Weinberg, who died a couple of years ago. In his 1977 bestseller, The First 3 Minutes, A Modern View of the Origin of the Universe, he famously wrote, it is almost irresistible for humans to believe that we have some special relation to the universe, that human life is not just a farcical outcome of a chain of accidents, but that we were somehow built in from the beginning. It's very hard for us to realize that the entire Earth is just a tiny part of an overwhelmingly hostile universe. The more the universe seems comprehensible, the more it also seems pointless. Weinberg's view is understandable. The universe is indeed inconceivably vast compared to the Earth and its inhabitants. The human race is indeed the outcome of a long chain of events that could have gone otherwise. The forces of nature, while not literally hostile to us, are certainly blind, unfeeling, and often harsh. The universe goes about its business without any concern for us. Isn't it foolish then, as Weinberg suggested, to imagine that we were somehow built in from the beginning and meant to be here? Hasn't the whole thrust of modern science, from Copernicus and Darwin down to the discoveries of the last century, been away from such naive anthropocentrism? Hasn't the story of science been about the, quote, successive dethronement of man, unquote, as the Harvard biologist and popular science writer Stephen J. Gould used to say? Well, maybe not. It's beginning to look very much like we may have, in some sense, been built in from the beginning, after all. In the last 50 years or so, particle physicists and others have begun to notice many features of the fundamental laws of physics and the structure of the universe that appear to be just what is needed for the existence of living things such as ourselves to be possible. These features are often called anthropic coincidences. Why are they called that? The word coincidence points to the fact, or claimed fact, that some features of the laws or structure of the universe happen to coincide with what is needed for life to be possible. The word anthropic comes from the Greek word for human being. It's not the best adjective to use because what is at issue in most cases is the possibility of living things of any kind, not just human beings. Until about 30 years ago, it was almost taboo to mention, let alone discuss, anthropic coincidences in the physics research literature. The idea that there might really be such coincidences, or if there were, that they had any significance, was generally dismissed out of hand as unscientific. There are a number of reasons for this. One was expressed rather frankly by a Nobel laureate in physics who declared that he hated the whole subject of anthropic coincidences because, quote, it smells like religion. Gradually, however, attitudes changed, in part because a number of leading physicists, many of them avowed atheists, including Steven Weinberg himself, began to take anthropic coincidences seriously as calling for explanation. It's now fairly widely admitted among particle physicists that some of these coincidences are real and may be telling us something important about the world. For example, Stephen Hawking and Leonard Mlodinow, in their 2010 popular book, The Grand Design, wrote, "What can we make of these coincidences? Our universe and its laws appear to have a design that is tailor-made to support us and, if we are to exist, leaves little room for alteration. That is not easily explained and raises the natural question of why it is that way." Edward Whitton, regarded by many physicists as the most brilliant theoretical physicist of his generation, and has called himself a skeptical agnostic on religious questions, said in an interview, "The laws of nature are very delicate. The fact that galaxies, stars, and planets, roughly like ours, could have formed, and that living things, roughly like us, could have formed, depends on many details of the laws of physics as we currently know them being just the way they are and not being slightly different. I think we'll never resolve the sense of wonder about that." Now, before going into the question of the possible significance of anthropic coincidences, it may be helpful to give some examples of them. Those who want to see more in-depth discussions and more details can refer to a number of technical articles, as well as, there are many technical articles now, as well as several popular books written by physicists. So I don't expect you to be able to read all that in a few seconds, but it'll be up on our website pretty soon. A famous anthropic coincidence has to do with the so-called strong force, one of the 5 known forces of nature. The others are gravity, electromagnetism, the weak force, and the Higgs force. The strong force is the one that binds neutrons and protons together to make atomic nuclei. If this force had been weaker by even about 25%, then we wouldn't be here. Why? Because it takes atoms of many types to make a living thing. The human body, for example, contains, I'm told, 25 elements, including hydrogen, carbon, nitrogen, oxygen, sodium, phosphorus, iron, and so on. Where did all these elements come from? Very early in the history of the universe, ordinary matter consisted of just isolated protons, neutrons, and electrons. A proton is the nucleus of the hydrogen atom, and here is a child's view of a hydrogen atom. So if there had remained only protons and neutrons and electrons, what would have happened is only hydrogen could have formed. They would only have hydrogen, and you can't make living things with just hydrogen to work with. To make all the other roughly 100 elements of the periodic table, protons and neutrons had to start sticking together to make the nuclei of atoms that are heavier than hydrogen. The picture at the top of this slide illustrates the idea. It shows protons as blue and neutrons as yellow. So looking at the top and going from left to right, first a proton and a neutron coming in from the left stick together to make a 2-particle nucleus called deuterium. Then we see a yellow neutron coming in from below and sticking to that to make a 3-particle nucleus called tritium. Then a blue proton is shown coming from above and sticking to that to make a 4-particle nucleus, which is the nucleus of helium-4, which for historical reasons is often called an alpha particle. In a similar way, larger and larger nuclei are formed by these fusion reactions all the way up to uranium nuclei, which have 92 protons and over 140 neutrons in them. This synthesizing of bigger elements out of smaller ones by nuclear fusion takes place largely inside stars. That's where most of the stable elements of the periodic table were and are made. And such fusion reactions release a lot of energy. That's what generates the energy of most stars. As you can see from this picture, the first step in this process of nucleosynthesis is one proton and one neutron sticking together to form a deuterium nucleus. If that first step cannot happen, then none of the later steps can happen, and then you are stuck with just hydrogen. And here's the thing. The strong force is just barely strong enough to allow that first step to happen. As I said, if it were only about 25% weaker, that step could not happen. Deuterium would not be bound, and there would be no life as we know it in the universe. What if the strong force had been a bit stronger than it is? In that case, it would have been strong enough to make two protons stick together. That cannot happen in the world we live in, but it would happen if the strong force were only about 2% stronger than it is. And two protons being able to fuse to make what's called helium-2 would have radically changed the way that stars like the sun burn their nuclear fuel. Now, in the past, people said, well, that would have made life impossible because you wouldn't have stars like the sun. Well, it's a little more complicated. There would have been stars who would have been quite different than the ones we see. It's a little hard to work out all the ramifications of that, but it's certainly questionable whether there would have been stars with the right properties to support life on their planets. So the strength of the strong force seems to be in a sweet spot, not too for life, neither too strong nor too weak. Another famous anthropic coincidence noticed in the 1950s by the astrophysicist Fred Hoyle has to do with the so-called 3-alpha process, which is the process that has produced essentially all the carbon in the universe. Now, this process, which takes place inside stars, involves 3 helium nuclei, or alpha particles, happening to collide at almost exactly the same instant of time and fusing to form carbon-12. Why do they have to collide at almost the same instant? The reason is that if 2 helium nuclei collide to form beryllium-8, beryllium-8 is highly unstable. In fact, they will only remain together for about 10 to the minus 16 seconds, and then they fly apart again. So, but if during that 10 to the minus 16 seconds that those 2 alpha particles are stuck together, a third one comes along at that sliver of time and hits them, those 3 can fuse together to form a stable nucleus, which is carbon-12. Now, as you can see, this is something that's not going to happen very often. And when Fred Hoyle initially calculated how much carbon would be produced by this 3-alpha process, he found that there should be much less carbon in the universe than is seen to exist, vastly less than is seen to exist. So that was a puzzle. And then he figured out the solution to the puzzle. He said, if the carbon-12 nucleus had an excited state at just the right energy, that excited state would enhance the 3-alpha process, resonantly enhance the process in such a way that it could happen much more readily and thus account for the abundance of carbon in the universe. But that excited state, that mode of vibration of the carbon-12 nucleus had to have just the right energy, within 1% or so. And if it was 1% or so higher in energy or lower, it wouldn't have worked, it wouldn't have enhanced the process, and there would be almost no carbon. And all life we know of is based on carbon. And as it turned out, he was right. The nuclear experimentalists then went out and measured the energy levels of the carbon-12 nucleus, and lo and behold, there was the energy level right where Hoyle predicted it. So that's a very famous one. An even more dramatic example of what's sometimes called anthropic fine-tuning was pointed out by myself and 3 collaborators and concerns a certain basic parameter called V in our present fundamental theory of particle physics, the so-called standard model of particle physics. V is short for the vacuum expectation value of the Higgs field. That's why people call it V. The parameter V is very important because it's like a knob that controls the masses of many subatomic particles, such as electrons and quarks, as well as the strength of the nuclear force. The strength of the weak force, and indirectly many other features of the physical world. As they show on this slide, the masses of electrons, the mass of neutrinos, the Fermi constant, which is the strength of the weak force, the mass of the pion, which actually controls the range of the strong force, and various other things depend on V in various ways. So it's a knob that controls a lot of things about the world. Now, if the value of V is much larger than it actually is in our world, if it were, then all neutrons, even neutrons inside atomic nuclei, would have been unstable to decay into protons. All the neutrons and nuclei would have decayed into protons. Nuclei would have been made of just protons, and they would then have been flown apart by the electrical repulsion of the protons in them. There would have been no stable nuclei except hydrogen. Now, why is it that neutrons would become highly unstable if V were significantly bigger? The reason, I'll go through that because I think it's maybe instructive to go through this in a little detail. The mass of the proton and the neutron are mostly come from the energy of the strong interaction, of the strong force. And they're very close in energy, as you can see. In certain common units, the neutron is 939 and the proton 938 in these units, the mass. The splitting in mass, and that's independent of V, or almost completely independent of this parameter V. But the splitting in mass between the proton and the neutron, the tiny difference in their mass, is controlled to a large extent by V. And if V were much bigger, the splitting between the neutron mass and the proton mass would become larger. Now, because the neutron's a little heavier than the proton, isolated neutrons are unstable. They will decay, as shown in the bottom. A neutron sitting there alone will decay into a proton plus some other stuff with a half-life of about 15 minutes. Now, that doesn't happen in nuclei. In nuclei, neutrons, in stable nuclei, neutrons can sit there forever because though you might gain energy by the neutron decaying into a proton, if it were to do that, it would rearrange the particles of the nucleus in such a way that it costs you more energy than you get because of what's called Fermi energy, because of the Pauli exclusion principle. So a neutron embedded in a stable nucleus is stable. However, if V is cranked up a significant amount, neutrons become so unstable that even in nuclei they would decay. And as I said, all of them would disappear from nuclei. You'd have only protons and nuclei, and that would have made all nuclei except hydrogen unstable to fission. Basically, the electrical repulsion of the protons would have blown the nuclei apart. Now, I've only told you a little part of the story of V. There's a lot more things go wrong depending on how big you make V. But if you make V actually bigger than it is seen to be in our world by about 40%, all sorts of bad things start to happen. And the bigger you make V, the worse the things that happen. But if it was maybe 40% bigger than we see it to be, we wouldn't have life as we know it. Now, what happens if V is smaller than we see it to be in our world? Well, then a completely different different disaster happens. There is a certain very subtle quantum process that can happen in our universe, but it's extremely rare. And they're called Sphaleron processes. They happen extremely rarely. But if you make V smaller than we see it to be, these Sphaleron processes would happen all the time, very readily, and erase all the protons and neutrons in the universe. They would all be wiped out. So you'd have no atoms of any kind. So V is in a sweet spot also, not too big and not too small. Now, not all, and I should say, a priori, just mathematically, the range that V could be in just mathematically would be allowed to be in this 57 order magnitude range. It has to be in a very narrow window there for life possible. And of course, it is in that window. Now, not all anthropic coincidences have to do with certain quantities being fine-tuned to have just the right values, like V and the strength of the strong force. Certain gross qualitative features of the universe and its laws are also important for making life possible. An especially important example is that the universe is governed by the principles of quantum mechanics. Quantum mechanics tells us that at very small distances, the physical world is grainy rather than smooth. The very fact that matter is made up of particles, such as protons and electrons, out of which complex structures can be built, including living things, is a consequence of this quantum graininess of matter. Moreover, the structures built out of those particles are only stable because of quantum mechanics. It is the fact that electrons act in a quantum mechanical way that prevents them from getting sucked into the nucleus. Have you ever wondered why the negatively charged electrons just don't get sucked into the positively charged nucleus and stay there? Quantum mechanics doesn't allow that to happen. Furthermore, even in a non-quantum mechanical universe, even if electrons could somehow be kept orbiting atomic nuclei rather than plunging into them, they would have an infinite number of ways of orbiting the nucleus. They could go this way, and they can go this way, and they can go in elliptical or very elongated orbits. There's an infinite number of ways for electrons to orbit the nucleus, given a certain amount of energy. And so no two atoms, even of the same element, would behave the same way. And an atom would look different, the same atom would look different at different points in time. Matter would be constantly and very rapidly morphing in unpredictable ways without stable properties. There would be not be solid things, but just mush. The ability of the universe to have life also depends greatly on the kinds of particles that exist and their properties. It's especially important that there are particles with the properties of electrons, neutrons, protons, pions, and photons, for example. Each plays crucial roles. The same is true of each of the known fundamental forces, which I listed before: gravity, electromagnetism, the weak force, the strong force, and the Higgs force. For example, electromagnetism holds atoms, molecules, and all ordinary matter together, and also gives rise to the existence of light. The strong force, as already mentioned, holds atomic nuclei together. Without it, nuclei would fly apart due to the electrical repulsion of the protons in them. The strong force also provides the nuclear fusion energy that powers stars like the sun, which in turn is needed to warm planets and generate and sustain life. Without gravity, matter would not condense into stars and planets, nor planets be able to retain their atmospheres. Moreover, the gravitational expansion of space and the gravitational clumping of matter in the early universe was key to generating the reserves of all the usable energy in the universe, which all life in the universe depends on. The weak force makes possible certain nuclear reactions that generate the energy of stars like the sun. The Higgs force is needed to give mass to particles such as electrons and quarks. It's not only the existence of all these forces, but their specific characteristics, their delicate and complex interplay, and the fact that their strengths are in just the right relation to each other that makes life possible, as the example I discussed of the stability of neutrons and nuclei illustrated, though there are many other examples. The characteristics of space and time are also critical. We take it for granted that there are 3 space dimensions and 1 time dimension. But there's no law of logic that says the world had to be made that way. Particle physicists study hypothetical universes whose spaces have different numbers of dimensions. Indeed, in superstring theory, which many experts think may be the correct unified theory of all the forces of nature, there are 9 space dimensions, 6 of which are curled up into little surfaces of subatomic size. It seems to be crucial for life that there are exactly 3 dimensions of space that extend for large distances, as in our universe. What if there were more than 3 extended space dimensions? If it were, then the force of gravity between two objects would depend on their distance from each other in a different way than the famous inverse square law of Newton. The force would depend on the inverse d minus 1 power, where d is the number of space dimensions. So, for example, if there were 4 space dimensions, the gravitational force would vary as the inverse cube of the distance. If there are 5 space dimensions, it would be the inverse fourth power of distance, and so on. That would mean that gravity at short distances would be relatively stronger than in our world, and at larger distance would be relatively weaker than Newton's law would say. And what that would mean is that planets would either get sucked into stars or fly off. You would not, it's actually an easy homework problem to show in a classical mechanics course, very easy elementary mechanics problem to show, that you couldn't have stable orbits of planets around stars in more than 3 space dimensions, if the law of gravity were otherwise the same. Same would be true of electrons. They would not be able to stably orbit nuclei. They'd either get sucked in or fly off. Now, what if there were fewer than 3 large space dimensions? What if we lived in a 2-dimensional universe? Well, then other things would happen that would be unpleasant. For example, it seems it would be hard to have complex neural circuitry, as seems to be needed for brains. You know, if you try to draw a complicated circuit diagram on a piece of paper in such a way that the wires don't intersect each other and cause short circuits, it's very difficult to do. In fact, there's an old puzzle that you give to kids, or at least ones who are interested in math, and you say there are 3 houses and there are 3 utility companies, water, gas, and electricity, and you just want to connect every house with every utility, but you want to do it in such a way that the connections never cross each other, and you can't do it. Okay. Now, in 3 dimensions, you can do it because the wires or the pipes or neurons can go around each other. They don't have to cross and short circuit and go around each other. So 2 dimensions, and even more 1 dimension, are so simple that it's hard to have complex circuitry, which you might need to have a brain, for example, or nervous system. So 3 dimensions of space is a very special number, it seems, if you want to have living things. Now, I've just given you a small sampling of the many anthropic coincidences that physicists have taught, and chemists and others have talked about. Remember, Ed Whitton, in the quote I gave earlier, said, there are many, many features of the laws of physics that seem to be just right. Now, what's one to make of this fact? One rather obvious possibility is that a mind framed the laws of this universe and did so with the intention that it should bring forth living things, including beings such as ourselves. That certainly accords well with the Christian view. There is, however, another way to explain at least some of these coincidences, which does not invoke God, and called the multiverse hypothesis. The multiverse idea is very speculative. There's no evidence for it, I should say, and it comes in a variety of versions. There are many popular misconceptions about the idea. First of all, it's not the same thing as the many worlds interpretation of quantum mechanics. It's a completely distinct idea. It also does not necessarily posit the existence of many universes, as is usually said. The versions of the multiverse idea thought about by physicists generally assume that the multiverse is a single universe governed by a single set of fundamental laws throughout. Now, in some versions of the idea, there are many versions of this idea, the universe can split and recombine, but nevertheless, those splitting and recombining universes nevertheless form a single interacting system governed ultimately by a single set of truly fundamental laws. So what makes a universe a multiverse is that the fundamental laws of that universe have a kind of flexibility that allows certain physical quantities and features that have been traditionally thought to be the same throughout the universe constants of nature, for example. They have a flexibility that allows these parameters or features to vary from place to place. For example, the strength of the strong force might be different in different domains of the universe. The types of particles that exist and their properties, the value of the parameter v, and so on, could be different in different domains of the universe. Now, those domains would have to be very far apart because we know that all of these parameters, like the mass of the electron and the strength of the strong force and so on, are the same throughout the whole part of the universe we can see, the so-called observable part of the universe. For billions of light years, we can see these parameters are the same to the farthest reaches of space that we can see. But we can imagine the universe is much bigger than what we can see, which is almost certainly the case. In those parts of the universe beyond what's called our horizon, perhaps these parameters take different values. Now, if there were a sufficiently large number of such domains, and these parameters varied over a wide enough range of values in those other domains, there could be a high probability that in some of those domains, all the physical quantities and qualitative features would be just right to make life possible. That's the multiverse idea. Basically, if you buy enough lottery tickets, one of them is going to win. Okay? Now, of course, to account for all the anthropic coincidences, the multiverse would have to be such that all the quantities and features that have to be just right for life would vary from place to place. And not only that, they would have to vary, as I said, over a sufficiently wide range of values to include the right values with some reasonable probability. In other words, the multiverse would have to be extremely rich in the possibilities that were realized in its various domains. Now, to many people, including many physicists, the multiverse idea sounds far-fetched and even kooky. Maybe even most physicists, maybe even most particle physicists would say that. Some religious people therefore imagine that it's just a desperate idea cooked up by atheists to avoid the obvious conclusion that the universe was designed with us in mind. But these dismissive judgments are not really fair. From the standpoint of our current understanding of fundamental physics, the multiverse idea is not at all as far-fetched as it may sound, and there are purely physics reasons to take it seriously. Now, given that there might be a naturalistic explanation of some of the anthropic coincidences, if the universe is a multiverse, does that mean that these coincidences don't in any way point to life being built in from the beginning? Are we back to the idea that we're simply accidents in a vast and pointless cosmos? I don't think so, for the following reason. In order for the universe to have a multiverse structure, the fundamental laws that govern it must have enough flexibility to allow many important physical quantities and features of the universe to vary from place to place. And that is a highly remarkable characteristic for the fundamental laws to have. There is no a priori reason to expect a universe to have laws that would make it a multiverse, let alone a multiverse with the enormous richness of possibilities you would need to make life possible, or at least reasonably likely. The takeaway lesson of the anthropic coincidences, therefore, in my view, is the following. If a universe is to be life-bearing, its laws must be very special in one way or another. They may be special in having many important features just right everywhere. Or they may be special in allowing all these features to vary from place to place in the universe over so many possibilities that somewhere in the universe they're just right. Therefore, we should not at all take it for granted that the universe is able to give rise to life. It did not have to be that way. Rather, it should be a source of great wonder that it is that way, as Edward Whitton, whom I quoted earlier, said. Now, having said all this, and this is the end of my talk, we remain with a question very troubling to many people. Why is the universe so big? How can we claim to be important in a universe that dwarfs us in its scales of space and time? There's at least a paradox here. Now, one answer is a very traditional one. The The universe was not made only for our benefit. As Psalm 19 declares, the heavens proclaim the glory of God. If it's the glory of God that they proclaim, there's no particular reason why they should have to be made to human scale. In fact, an important thinker of the 15th century, Cardinal Nicholas of Cusa, argued that a universe of infinite extent would more aptly reflect the infinite splendor of God. That's a good answer, but there's another, based on physics. It turns out that the very age and vastness of the universe themselves have anthropic significance. Life emerged in our universe in a way that required great stretches of time. Most of the elements needed for life were made deep inside stars, which had to explode and disperse those elements into space to make them available to be formed into planets and living things. That alone required billions of years. Biological evolution required billions of years more. Thus, the briefness of human lifespans and even of human history compared to the age of the universe may be simply a matter of physical necessity, given the developmental way God seems to prefer to work. It takes longer for a tree to grow to maturity and to be able to bear fruit than the fruit of the tree lasts. It took much longer for the universe to grow to maturity, so to speak, and be able to generate life than a human life lasts. Physics also suggests why the universe has to be so large. The laws of gravity discovered by Einstein relate the size of the universe in space and in time. The fact that the universe is many billions of light years across is a direct consequence of the fact that it has lasted for several billion years. Perhaps we would be less daunted by a cozy little universe that never got larger than, say, the size of Asia or North America. There's plenty of room for us to cavort in. But such a universe would have lasted for only a few milliseconds, according to Einstein's equations of gravity. Even a universe that never exceeded the size of the solar system, which is vast compared to human scales, would have lasted for only a few hours, a matter of hours or days. A universe constructed in such a way as to evolve life had to extend vastly in space as well as in time. So that frightening expanse of space that so often is said to be a sign of human insignificance is actually a precondition for our existence, given the way the laws of physics work. And so, like many other features of our strange universe, the vastness of the universe points to man, as it also proclaims the glory of God. Thank you. I think there's microphones. I forgot to ask. There's microphones to people to ask questions. But you can shout out a question. I'll call on you. Yeah. Now shout it out loud, and I'll repeat it if necessary.
I've struggled in our conferences to draw the line between the dangerous God of the gaps idea and things that are simply wonderful.
Mm-hmm.
So when you think about this topic in terms of growing in wonder, do you ever worry about crossing over into a God of the gaps type idea where, since we don't know why it's like that, then maybe we're putting God there?
Right, and that's why in my book, Modern Physics, Ancient Faith, and in this talk, I avoid the step that I think too many people make of saying, oh, here are all these coincidences, therefore that proves that someone designed the laws of physics precisely to make our existence possible, so God exists, QED. I don't think we shouldn't try to prove more than we can prove. And nevertheless, it is remarkable. So I regard this as a sort of defensive move a little bit, a parry. So remember, Weinberg, and not just Weinberg, argued the more we know about the universe, the more pointless it appears. As we've learned more about, and this is a standard narrative which we've lived with for hundreds of years, The more we've learned about the universe, the more pointless the universe appears, the more we appear, as Bertrand Russell said, to be a curious accident. We're a fluke. I can take those, Sean. But they, of course, also are not claiming to prove this, that we're an accident. They just say that's what the evidence seems prima facie to point to. And what I think what we can say in response is no, actually prima facie, on the face of things, if anything, the laws of nature and the structure of the universe seem to point to our existence. It doesn't prove anything, but it seems more to point that way than the way the atheists have traditionally said. And I take pains to say, don't laugh at this multiverse idea. It's not a foolish idea. And I actually think it does. There are some anthropic coincidences that we do sort of know the explanations of. And so I think some of them, maybe many of them, have conventional physics explanations. Nevertheless, I do think the takeaway lesson is not any old, if you had some cosmic physicist cooking up laws of physics and suggesting them to God, here, make a universe based on this one or on this one. Most of them would be duds, that is, they wouldn't give rise to life. It's actually quite remarkable. You need very special laws to have a universe with things as complex and sophisticated as we are to be possible. And that is something that we should not only wonder at, but it is a remarkable fact, and I think it's valid to say that at least it's a little piece of evidence that we're not flukes. Father Javier. Here.
So thank you, Steve. Can you hear me?
Yeah.
Yeah. Okay. So I was wondering, I was seeing that you are approaching the Darwinian reasoning with universes instead of living beings somehow. Mm-hmm. Because the flexibility, it's an idea that I like very much, but it's like there's random mutations that occur in living beings, and we would have some selection that in our case is our very existence. My question is, if you want to avoid the pure randomness argument, so the lottery argument, right, you need to refer to something else in this flexibility. So you need to show something that I think Liz Molin refers to as typicality. Mm-hmm. Somehow we should show how the universe, perhaps within a bigger multiverse, the universe we live in is typical somehow. Otherwise, we are not doing the right science. You know, the argument of typicality, so we cannot get back to the idea of sheer randomness. Do you think it's possible to show that typicality with the laws of nature, with this flexibility, somehow they are, biased through this emergence of life?
That the laws are biased towards the emergence of life. You're not talking about whether the laws among all possible mathematical laws of physics are typical, or you're saying, given these laws, is it typical to have life?
So there's an attractor in the possibilities of values for the concept of nature. There's an attractor to a universe where life is present.
Now, if you have a universe, if we're not in a multiverse and the constants of nature, the mass of the electron and so forth, are what they are throughout the universe, and that's just a condition, that's part of the laws of physics, period, then I don't see any room for an attractor. If the constants of nature could evolve with time, if, for example, the strength of the strong force of the parameter V, or the mass of the electron, and all those things were not only variable, but actually had some kind of dynamics that allowed them to evolve over time, is it possible that that could be true and that they also are somehow attracted to those values that allow life to be possible? Actually, it's a lot harder to cook up laws of physics where things like that vary with time and then reach a value and stay there. It's much easier to make laws of physics where they have one value over here and one value over here, the multiverse idea. Having them evolve towards and then freeze at some value for billions of years is very hard to do. So, but that would all simply be a version of the anthropic idea. And so you would replace domains. You would have there'd be parts of the universe where the mass of the electron went to one value, and that was a dud. And then over here, it might go to a different value, and that's propitious for life. And then you'd have only place you'd have people around to measure these values would be the ones where they had just the right value. This is really a version of the multiverse idea. But as I said, it's harder to build a multiverse where these things are changing with time than it is to just make them have different values in different places. There's someone behind you. Yeah, can't see you.
Thank you. That was a great talk.
Thanks.
I'm just wondering, is the multiverse really an explanation for fine-tuning, or doesn't that just push the problem back one step? Because the multiverse itself, right, requires explanation.
Yeah.
And there has to be fine-tuning to generate.
I'm not sure. Yeah, I that's sort of what I'm saying. That in a way, if you have the fundamental laws, the truly bedrock laws of physics, be such as to have this kind of flexibility, that is itself a remarkable thing, which you could regard as an anthropic coincidence in itself. So I agree with you on that. Though I'm not sure whether that would require fine-tuning. It might. But, well, to give an example of what you're saying, one of the anthropic coincidences, and I better stop after this because it's getting late, one of the things that people point to is the universe was remarkably flat spatially. This three-dimensional space is very flat in our universe, and if you go back towards the time of the Big Bang, it was astonishingly flat to many decimal places. Meaning that if you drew a big triangle in space, the angles add up to 180 degrees to like 30 decimal places. It had to be, now why? It turns out that had to be the case. The universe had to be astonishingly flat early on, or we wouldn't be here. Universe would have, things would have gone haywire. But we do know, we don't know. We have a very good explanation of why the universe was so flat early on. It's called inflation, something called cosmic inflation. There's a lot of reason to believe that idea is true. So we have a conventional physics explanation of why the universe was so flat. On the other hand, actually to get inflationary theories to work at the present moment, and I don't think this will always be the case, but all the theories have been proposed to give you an inflationary universe early on, require a certain amount of fine-tuning. Not 30 decimal places of it, but some. So it could be, yeah, that could be the case, what you're saying. But I agree with the thrust of what you're saying, which is you're pushing the problem back. Then you have to say, why do the laws have this remarkable feature that they give you a multiverse? That itself is an astonishing thing. But I think I better stop there so we can have a break. And then Dan Keebler, who's the vice president of SCS, is going to be chairing the rest of the morning session.